Okay, next we're going to look at a little bit of notation and do some wishy-washy kind of moving into why this integral notation is what it is, this little curvy S that we've been working with. And so what we have is if the width of a rectangle, we're going to call the width of those rectangles we've been working with delta x, change in x, a small change in x. Well, we've learned that we want the width of the rectangles to be really small. The smaller they are, the more rectangles we have, and the better the approximation is. So we've talked about summation notation before. Then what we would have is we want the sum of all the rectangles we've created. Well, how do we find the area of the rectangles? Well, we take the height of the rectangle, which is the y value on that function, and multiply it by the width that we're making those rectangles, delta x. Again, we want delta x to be as small as possible. And we take the sum of n rectangles, however many rectangles we have, with height y on the curve and width x, or delta x is what we're calling it. And so the actual area of the curve under the curve is going to be the limit of this function above as delta x goes to 0, as the width of the rectangles gets smaller and smaller and smaller. Essentially, we want the width of those rectangles to be infinitely small. We want millions and millions of little tiny rectangles that we're finding the area of, and then the width of them approaches 0 eventually. And my big wishy-washy jump is that this kind of turns into our integration symbol that we use. It's kind of like this E here, which is the summation. It's the sigma, the Greek sigma, becomes like an elongated S, which is sort of like this integral symbol here. And the delta x becomes the dx at the end. So notice this delta x here kind of becomes the dx. And what this integral symbol means is it means we are finding the sum of underneath that curve y, as the width of those rectangles approaches 0. And so that's kind of all of this kind of becomes our integral, which is our calculus part, that limit part. Okay, we're going to do 2 problems, then we'll be finished. If I can stop.